Okay, so this video is for section 3.8, and what we're going to be doing is we are going to be using our derivatives to solve related rate problems. So these are going to be word problems, so it's going to be putting everything together pretty much that we've learned. So step number one, you want to make sure that you read the problem very carefully, and sometimes it's really helpful to make a sketch of the information. The other thing that is really key with this is you want to identify any of the rates that you're given and the rate that you're trying to figure out. So we're going to have to write at least one, maybe more equation to express the relationship between the variables. And we're going to introduce the rate of change by differentiating the appropriate equation with respect to time, t. Okay? Then the next step is to substitute in any known values and solve for the desired quantity. And then the very last thing, you just want to check to make sure that it all makes sense. Okay, so let's go ahead and do an example. So example number one, we have an oil rig and it springs a leak in COMCs. The oil is going to spread out in a circular pattern around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? Chloe, watch it. Sorry, that was my cat. Okay. Show you the camera. All right, so first, let's see what we have going on here. We have a circular patch. Okay, so circular patch, that makes me think of a circle. Okay, and the radius is from the center to the edge. The radius increases at a rate of 30 meters per hour. Okay, so what that is telling me is dr dt is 30 meters per hour. Okay, so radius with respect to time is going to be, the rate is going to be 30 meters per hour. The other thing that is important with this is we care about area, and I know that the formula for the area of a circle is pi r squared. And then the very last thing they tell us is they want to find out how fast the area is increasing when the radius is 100. Okay, so r equals 100 meters. Okay, so this is all of my given information up here. So what we're going to need to do is we are going to use the formula for the area of a circle, and we are actually going to take the derivative of that with respect to time, because we want to know how fast the area is increasing. Okay, so my formula is area is pi r squared. So I'm going to take the derivative of A with respect to time. And on the right side of my equation, when I take the derivative here, it's the 2 is going to come in front, so I'm going to get 2 pi r, and that's the derivative of r with respect to time. So in both cases, I'm taking the derivative with respect to time of my variables. So now what you should be noticing is I already know what dr dt is. Dr dt is 30 meters per hour. I also already know what my radius is. My radius is 100 meters, okay? So now I'm just going to substitute all of that in. So we're going to get 2 pi times 100 meters times 30 meters per hour. And if I multiply my 2 with my 100 and my 30, I will get 6,000 pi meters squared per hour. Okay. And that's my answer. All right, let's do another one. Okay, so example 2. We have two small planes that are approaching the airport. One is flying due west at 120 miles per hour. The other is flying due north at 150 miles per hour. Assuming they fly at the same constant elevation, how fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 225? Okay, so first, I'm going to draw a little picture, but let me remind you that nobody eats soggy waffles. Okay, so we have a northbound plane, so that's going up, and we have a westbound plane, so that's going towards the right. Okay, so if I were to make a triangle, we have our northbound plane and our westbound plane, and they're flying to the airport. So here's the airport. Okay, and when I totally drew that backwards because we're driving to the west, not driving, flying to the west. Here we go. Okay, so there's my west plane is going to the west, and my north is going up. Okay, fantastic. Okay, so let's see, what else do we know? We know that the westbound plane is going at 120 miles per hour. Okay, so what that is telling me is the derivative of the westbound plane with respect to time is going to be 120 miles per hour. Okay. We also have the north plane. The north plane is 150 miles per hour. So that's telling me the derivative of the north plane with respect to time is 150 miles per hour. Okay, what else do we know? We want to figure out how fast the distance between the planes is changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport. Okay, so if I'm looking at this, this is my north plane. Okay, so my north plane is here and it is 225 miles away from the airport. And my west plane is here and it is 180 miles away. All right, so hopefully you can tell that I need to know what this distance right here is, because this distance is telling me how far apart the planes are from each other as they come together to go to the airport, okay? So you might have noticed that this is a triangle and it's a right triangle specifically. So we could do Pythagorean theorem in which the two sides squared is going to equal my hypotenuse squared, okay? So essentially I'm doing north squared plus west squared is going to give me x squared. So north was 225 miles, west was 180 miles. Okay, so if I add those together, I am going to get that 83025 is x squared. And I'm just going to leave it like that for right now, not take the square root because I don't want to round if I need to. Okay, so the next thing that I want to draw your attention to is I'm going to rewrite what I used for Pythagorean theorem, the north squared plus west squared equals x squared. So north squared plus west squared equals x squared. Okay, so we're going to take the derivative of each of these with respect to time, okay? So the derivative of n squared is going to be 2n dn dt, plus the derivative of west is going to be 2w dw dt. And then my derivative of x is going to be 2x dx dt. Okay, so we are trying to figure out what dx dt is, okay? Now, one thing that I didn't put on before, if you were thinking about this picture as a coordinate plane, the airport would be 0, okay? So since my two planes are traveling back towards that airport, the 120 miles and the 150 miles are actually going to be negative because they're going back to the airport, back to 0, okay? So with that in mind, we can now plug in the information we know into this formula. We know that the north distance was 225 miles. So I'm going to now substitute in all of my variables. So 2 times 225 times my dn dt, which was negative 150, plus 2 times my w, 180, times negative 120, is going to equal 2 times x. Okay, so x squared was 8,300, or sorry, 83, oh my gosh, 83,025. So if I just want x, because that was x squared, I'm going to do the square root of 83,025. I'm not sure why that one's so hard for me to say. Dx dt. Okay, so now we just need to solve that. So if I take care of this whole left side, I'm going to get negative 110,700 equals this x dt. And then I'm going to divide by that. And then I'm going to get about 192 miles per hour is dx dt. So what this is telling me, it's telling me as my planes are coming back together, the distance between them is negative 192 miles per hour. And that makes sense that it's negative because the distance should be getting smaller as they approach the airport. Okay, what's my answer here? Okay. Next example. Okay, example 3. Sand falls from an overhead bin, accumulating into a conical pile with a radius of that is always equal to 3 times the height. If the sand falls from the bin at a rate of 120 feet cubed per minute, how fast is the height of the sand pile changing? Okay. So one thing I want to point out, this should be cubed. I think when I copied it over, it did not copy nicely. Okay. So let's see, we have a cone, okay? So I'm just gonna draw, so it's like we have a circle at the bottom and it's like, imagine that this is all filled in, but no, you know, you're working with me and I'm gonna, you know, not judge my picture. Okay, so in the cone, this is my radius and this is my height, okay? So one of the things that I know about a cone, we're doing volume in this case because the sand is filling it up into this pattern. The volume of a cone is 1/3 pi r squared h. Okay, so that's important. The other thing that is important is it's telling me that the radius is always 3 times its height, okay? So that means that your radius is going to equal 3h. Okay, what else do I know? We want to know how fast the height is changing when the pile is 10 feet high. Okay, so that's telling me my height is 10 feet. And then my rate is 120 feet cubed per minute. Okay, so what this is telling me is the derivative of my volume with respect to time is going to be 120 feet cubed per minute, okay? All right, so let's see what we got going on here. This one has a lot of different pieces, right? So I am going to take the derivative of this with respect to time, okay? Because then that's going to give me dv dt, all right? We are trying to figure out how fast the height is changing, okay? So let's go ahead and take that derivative first, and then we'll see what we can substitute in. All right, so I'm going to write the formula down first. So volume is 1/3 pi r squared h. Okay, so before I take the derivative, I want to first simplify this right side of my equation so that I don't have an r and an h on the same side, okay? So we know that the radius equals 3h. So instead of writing radius, guess what? We're going to write 3h. Okay, so let's clean this up before we do anything else. All right, so we're going to get volume is 1/3 pi. 3 squared is going to be 9, and h squared times h, which is going to end up giving me h cubed, and 9 times 1/3 is going to give me 3. So volume equals 3 pi h cubed. Okay, now that we have that, let's go ahead and take the derivative. Okay, so dv, derivative of volume with respect to time, is going to be, all right, so 3 times 3 is going to be 9. And then my h is going to be squared. And that's the derivative of h, the derivative of my height with respect to time. Okay, so now that we're here, we are trying to figure out how fast the height is changing. But we know dv dt is 120 feet cubed per minute. So I can actually substitute that in. We also know that the height is 10. Okay, so let's plug that stuff in. So we're going to say 120 feet cubed per minute, that was dv dt, is equal to 9 pi 10 for my 10 feet. Oh, you know what I didn't write down and I said I did? My squared. Squared. All right, so remember I said it, but I didn't write it down. 3 times 3 gave me 9, but the h should still be squared because 3 minus 1 is 2. Okay, so 9 pi, height is 10 squared, dh dt. So we're solving for dh dt. Okay, so let's take care of this whole right side. We're going to get 900 pi dh dt equals 120 feet cubed per minute. And this is feet. I should have put my units, and feet squared from my squared. So now I'm going to divide by 900 pi feet squared. Okay, so this is going to reduce down to 2/15 pi. And since I have 3 feet at the top and 2 at the bottom, I'm just going to end up with 1. And that gives me my dh dt. So the height is changing at a rate of 2/15 pi feet for every minute. So I feel like with these problems, sometimes I think it's a little bit overwhelming to know where to start, but if you always start by writing down your given information and drawing a picture, I think that really does help a lot. Okay, we got 3 more examples that we're going to do together. So we have an observer that is standing 200 meters from the launch site of a hot air balloon. The balloon is rising vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after the launch? Okay, so we have our hot air balloon. Ooh, this is pretty good. All right, so hot air balloon. And then we have an observer that is 200 meters from the launch site. Okay, so here's going to be my launch site. And then the observer is 200 meters away. Okay. The balloon rises vertically at a rate of 4 meters per second. Okay, so I'm going to turn this into a triangle, and I know it's going to be a triangle because it wants to know the angle of elevation. Okay, so the angle of elevation is actually here. This is a throwback to your geometry days when you did trig. So the angle of elevation is how far the angle is of the observer looking up at the balloon. Okay, and it's changing. The balloon is rising vertically at a rate of 4 meters per second. So I'm going to call this h for height. So then my change in height over time, so dh dt is going to be 4 meters per second. Okay. How fast is the angle of elevation of the balloon changing after 30 seconds? Okay, so my time is 30 seconds. And the 30 seconds can actually tell us how high the height is, because it goes at a rate of 4 meters per second. Okay, so if I do 4 meters per second times 30 seconds, that's going to give me 120 meters. Okay, so my height is 120 meters. Okay, so what I want you to think about is, when you're thinking about your trig days, that this is a right triangle, and this is my hypotenuse, this is my opposite, and this is my adjacent. Okay, so which of your trig ratios uses opposite and adjacent? Hopefully you're telling me it's tangent. Okay, so generic rule for tan is opposite over adjacent. Okay, so let's fill in. Tan of my angle is equal to, I'm just going to leave this as height for right now because I want to keep it generic so that I can then take the derivative. Okay, so we're going to take the derivative with respect to each side. So the derivative of tangent is secant squared, and that is the derivative of theta with respect to time. And here, the derivative of my height, since that's just a generic thing like x, the derivative of x is just 1, the derivative of my height is just 1. My 200 meters is a constant in front of that, so that's going to stay the same. And that is the derivative of the height with respect to time. Okay, so now we're going to have to plug in our information, and we're going to have to make sure that we have everything first. So we know dh dt is 4 meters per second. Okay. So one of the things that we did not do is we did not solve for our angle. Okay, so what I want you to think about is the fact that we have secant, right? And secant is essentially the same. So secant, remember, is the same as like 1 over cosine theta, right? Oh, that's really light. Let me switch colors to something a little bit darker. Okay. So, and cosine, you know, if I had cosine of theta, it would be adjacent over hypotenuse, right? Which means since secant is 1 over cosine, that it's going to be the opposite of that. So secant theta is going to be hypotenuse over adjacent. Okay, so if I go back to my picture up here, I'm missing my hypotenuse, but I could figure it out because this is a right triangle. Okay, so let's go ahead and do that. We're going to say 120 meters squared plus 200 meters squared equals my hypotenuse, which I'll just call C squared. Okay, so if I do this whole thing, I'm going to end up with my hypotenuse C is equal to the square root of 54,400. Okay. All right, so since that's my hypotenuse, I know that secant theta is going to equal 54,400. Okay, let me just rewrite that. The square root of 54400 divided by my adjacent. So my adjacent in this case is 200. Okay, so now I can actually plug that in here, except I'm going to need to square it. Okay, so square root of 54,400 over 200 squared d theta dt equals 1 over 200 meters times 4 meters per second. Okay. All right, so then if you do that, you are going to end up with I just wrote down the answer. I didn't write anything else down. Okay, so this side over here is going to end up being the 54,400 over 200 squared. Okay. 4,000. 40,000, not 4,000. D theta dt equals 4 over 200. Meters are going to go away, and this is just going to be seconds. And then we're going to end up dividing by this. So when you do that, you will end up with d theta dt. So my angle is changing with respect to time at a rate of 1 over 68 radians per second. Okay. All right. So that was a nice example. That one had a lot of different pieces. Let's do one that's less involved. So we have the edge of the cube is increasing at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? Okay, so you know a cube is essentially like a 3D square, and each of the edges of the cube are going to be the same. Okay, so the formula for the volume of a cube, it's essentially like a rectangular prism where you have length times width times height, except the length, the width, and the height are all the same. So we're going to call that edge E cubed. We know that the edge is 50 centimeters, and we know that the rate, so dE dt, is 2 centimeters per second. Okay, so what we're going to do is we are going to take the derivative of the volume with respect to time. Okay, so I'm going to write my volume down. So volume equals E cubed. So dV dt is going to be 3E squared dE dt. Okay, so now we just have to plug it in. We know that our edge is 50. We know that dE dt is 2 centimeters per second. So 3 times 50 centimeters squared times 2 centimeters per second means that dV dt, the change in volume with respect to time, is going to be 15,000 centimeters cubed per second. Done. All right. See, that one was pretty nice. Okay, one more. Okay, so we have a fly fisherman, and the fly fisherman hooks a trout and begins turning his circular reel at a rate of 1.5 revolutions per second. Circular. If the radius of the reel and the fishing line on it is 2 inches, how fast is he reeling in the fishing line? Okay, so this one's going to be a little bit more involved, okay? So the dr dt is going to equal 1.5 revolutions per second. Okay, so that's the rate that I'm given, all right? The circular reel, if you think about it, we are essentially, he's like winding it up, okay, and it's going around the edge of the circle, so that means it's going to be circumference that I'm dealing with, and the formula for the circumference of a circle is 2 pi r. Okay, the other thing that is important is that we have the radius, which is 2 inches, and also that's the length of the wheel on it as well. So my length is also going to be something I care about. So I'm going to call length L. We're also going to use a big R to stand for the number of revolutions that I have. Okay. All right, so let's just recap this real quick. The fisherman is rolling it up at a rate of 1.5 revolutions per second. When we're rolling it up, we consider that circumference because it's going around the circular part of the fishing rod. The radius is 2 inches. We also care about the length, and we care about R being the number of revolutions, okay? So in essence, the length of the line is going to equal revolutions times circumference, okay? We know the formula for circumference, so let's go ahead and plug that in. So length times 2 pi radius, okay? The other thing that we know is we know what the radius is. We know the radius is 2, so let's plug that in. All right, so simplify. So we're getting r times 4 pi, okay? Now that we're here, we're gonna go ahead and take the derivative of the length of the fishing line with respect to time. Okay, so r is my variable in this case. So the derivative of r is just going to be 1. So that means I'm just going to be left with 1 times 4 pi, which is 4 pi. And we know the rate at which the fisherman is reeling this up is 1.5 revolutions per second. So I can substitute in dr dt. So we're going to get dl dt equals 4 pi times 1.5 revolutions per second. And that is going to give me 6 pi inches per second. Okay.